Tonight, we're going to explore the sun. Out there, its outer atmosphere burns hundreds of times hotter than its surface. A year ago, NASA's Parker solar probe flew into the sun, into a place that defies physics, and what it touched there, we still can't fully explain. So drift with us slowly toward that pale, glowing crown of light. By the end of tonight, you'll understand exactly why. Because tonight, we'll follow that little spacecraft all the way in. We'll meet the man who predicted the solar wind long before anyone believed him. We'll sit quietly with the impossible heat of the corona, that pale, ancient crown of light. We'll watch the probe fall for 6 years toward the fire, go silent one Christmas Eve, and send back a single tone to say it lived. And we'll drift through what it found out there, close enough to touch a star, and still humbled by how much it keeps to itself. We didn't come back with every answer, but that's all right. There's nothing to solve tonight, only somewhere gentle to wander. To understand why anyone would ever build a machine to fly into a star, we have to go back to a time when almost no one believed there was anything out there to fly into. For most of human history, the space between the sun and the earth was imagined as a kind of perfect emptiness, a clean, silent vacuum. Light crossed it, of course, and warmth arrived the way it always had, soft on the skin in the morning. But the gap itself, the 93 million miles of darkness between us and the star that feeds us, was thought to be utterly still. Nothing moving through it at all, but light. Picture that older idea of space for a moment, because it is a peaceful one. A still pond on a windless evening, the surface like glass, nothing stirring. That was how the solar system was imagined. The sun as a lamp hanging in the middle of a great quiet room, and the planets drifting around it through air that never moved. For a long time, that picture seemed entirely reasonable. There was no obvious reason to think otherwise. The sun was a fire in the distance. We were a small world that circled it, and in between lay nothing worth a second thought. Consider this too. For most of human history, no one even knew what the sun was made of. It was simply fire, a great lamp hung in the sky, its substance a mystery as deep as the space around it. It was not until the 1920s that we truly began to learn, and the answer came from a young astronomer named Cecilia Payne. Studying the light of the stars for her doctoral work, splitting it into its colors and reading the faint fingerprints hidden there, she arrived at a startling conclusion. The sun was not made of the same heavy stuff as the Earth, as nearly everyone assumed. It was overwhelmingly hydrogen and helium, the two lightest and simplest elements there are. The sun was, in essence, an enormous glowing ball of the lightest gas in the universe. It was such a radical idea that the senior scientists of the day pressed her to soften it, to set the result aside as probably mistaken, because it disagreed so completely with what everyone believed. She did, gently, for a time. And then, within just a few years, others confirmed that she had been exactly right. The sun and the stars, and very nearly all the visible matter in the cosmos, are mostly hydrogen. It is now considered one of the most important discoveries in the history of astronomy, made by someone who, like Eugene Parker after her, saw the truth a little before the world was ready to agree with it. The sun, it seems, has a quiet habit of being stranger and simpler than we expect, and we have a quiet habit of arguing with it before we finally listen. And yet, there had always been one small, strange clue hanging in the night sky, that the room was not as still as it looked. The clue was comets. For thousands of years, people had watched comets drift across the heavens, trailing their long, glowing tails. And somewhere along the way, careful observers noticed something curious about those tails. They did not stream out behind the comet the way you might expect, the way a scarf trails behind a runner. Instead, a comet's tail always pointed away from the sun. Always. Even when the comet was moving away from the sun, its tail ran out ahead of it, blown backward, as though some steady wind were forever pushing it away from the star. In the 1950s, an astronomer named Ludwig Biermann sat with that simple fact and took it seriously. If a comet's tail is always pushed away from the sun, he reasoned, then something must be doing the pushing. Not light alone, which was too gentle to explain it, but something with substance. A stream of particles, perhaps, pouring out from the sun in every direction, strong enough and constant enough to blow the delicate tails of comets always outward, like windsocks pointing down a road. It was a quiet observation, the kind that is easy to overlook. But it was a thread, and a young physicist was about to pick it up. His name was Eugene Parker. He was working at the University of Chicago, still early in his career, when he started turning over an idea that most of the senior figures in his field would have called politely a little absurd. He had been studying the sun's outer atmosphere, that faint crown of light we met a few minutes ago. And the more closely he looked at it, the more convinced he became that it could not simply be sitting there glowing, holding still. Something about it, he thought, had to be flowing. And the comets, with their backward blown tails, seemed to agree. By every account, Parker was a patient and careful man, more comfortable with a quiet calculation than with an argument. He was not the sort to make grand claims for the sake of attention. He simply followed the mathematics where it led him, slowly and stubbornly, even when it led somewhere no one wanted to go. And in this case, it led somewhere genuinely radical. Parker's reasoning was the kind of thing you can almost feel, rather than only follow. The corona, he knew, was astonishingly hot, so hot that the gas within it could not possibly hold itself in place. Heat, after all, is motion. The hotter something becomes, the more violently its particles move, the harder they push against whatever tries to contain them. Think of a kettle coming to the boil, the lid beginning to rattle and lift as the steam inside grows restless. The corona was like that, except there was no lid, and there was no kettle. There was only the sun's gravity, trying to hold the hot atmosphere down. And the corona, Parker realized, was so hot, so restless, that the sun's gravity, for all its enormous strength, simply could not keep a lid on it. So the outer atmosphere would not stay put. It would leak. It would stream away from the sun in every direction at once, a constant, gentle exhale of material pouring out across the solar system, never stopping, never running dry. It would, in fact, be exactly the steady outward stream that Biermann's comets had been hinting at all along. He gave this idea a name. He called it the solar wind. It is worth sitting with that phrase for a moment, because it sounds softer than what it actually describes. When we say wind here on Earth, we mean moving air, a breeze through the trees, a breath against a window. The solar wind is something else entirely. It is not air, it is plasma. Plasma is sometimes called the fourth state of matter, and it is by far the most common one in the universe, even though we rarely meet it gently in daily life. Let me walk you up to it slowly, because it is a lovely idea. You already know 3 states of matter without ever thinking about them. There is solid, like the ice in a glass. There is liquid, like the water it melts into. And there is gas, like the invisible vapor that rises when that water boils away. Each step is just the one before it, with a little more heat added, the particles loosening their hold on one another, moving more freely each time. Plasma is simply the next step up that same ladder. Take a gas and pour in even more energy, more heat, and eventually the atoms themselves begin to come apart. Their outer pieces, the tiny charged particles called electrons, are torn loose and set free, leaving behind a glowing soup of charged fragments. That electrically alive state is plasma. It glows. It responds to magnetism. It behaves in ways that ordinary air never could. And it is everywhere. It is what the sun is made of. It is what the stars are made of. Nearly all the ordinary matter in the visible universe is plasma. We simply live in one of the rare, cool, quiet corners where it is uncommon. And it was plasma, Parker said, that was flowing out past the planets all the time in a steady stream. And though plasma is rare in our cool corner of the universe, you have seen it more often than you might ever guess. A bolt of lightning splitting the sky is a brief, jagged thread of plasma. The air itself torn apart by electricity for a fraction of a second. The soft glow of a neon sign in a shop window is plasma, gas made to shine by a current running quietly through it. The hottest part of a candle flame flickers at the very edge of becoming it. And the northern lights, those slow curtains of color we will return to later in the night, are plasma too, the breath of the sun glowing gently as it meets the air. This stream does not drift, it races. The solar wind pours away from the sun at hundreds of miles every second, and its fastest gusts cross 1,000,000 miles per hour. It rushes past Mercury, past Venus, past the Earth, washing over each world in turn before continuing on toward the distant edges of the solar system. Right now, tonight, while you lie still, it is passing the Earth. It always is. The space around our planet is not empty and never was. It is alive with the wind from a star, blowing softly and endlessly through everything. A breath that has never once stopped in all the long life of the sun. That was Parker's idea, a continuous wind of plasma, blowing from the sun across the entire solar system. The still pond turned out to be a flowing river all along, and the response from the scientific world, at first, was disbelief. This is the part of the story that I find the most human and the most comforting. So let's take it slowly. When Parker wrote up his theory and submitted it to be published in a respected astrophysics journal, 2 reviewers read it carefully and recommended that it be rejected. They could not find an error in his mathematics. The numbers held together, but the conclusion simply felt wrong to them. It contradicted what everyone understood about the calm, empty space between the planets. It asked them to believe that the still room they had pictured all their lives was actually full of a racing wind, and so they advised against printing it. It would have been easy for the idea to quietly disappear there, the way many good ideas do, set aside not because they are mistaken, but because they are early. Science is full of such moments, ideas that arrive a little before the world is ready to receive them and slip away unheard. But the editor of that journal was a man named Subrahmanyan Chandrasekhar, himself one of the great minds of the century. And when the rejections came across his desk, he did something simple and quietly brave. He read the paper again. He looked for the mistake the reviewers were certain must be hiding in it, and he could not find one. The reasoning was sound, even if it was uncomfortable. So he set aside the objections, and he published it. That decision did not make Parker right. It only gave his idea a chance to be tested. And being tested is a slow business in science, the kind of thing that can take years, sometimes a lifetime. For a while, Parker simply had to live with being doubted, to hold an idea he believed was true, and to wait while the people he respected most quietly assumed he was mistaken. There is a particular loneliness in that, in knowing something before the world is willing to know it with you. But there is also a kind of quiet faith in it, the patience to let the truth arrive on its own slow schedule. Then, a few years later, the waiting ended. In 1962, a small NASA spacecraft called Mariner 2 set off across the inner solar system on its way toward Venus. And as it traveled through that supposedly empty space, its instruments measured something steady and unmistakable. A continuous flow of charged particles streaming outward from the sun. Exactly the wind Parker had described. Not a fluke, not an occasional gust, but a constant presence, filling the space between the worlds, just as the comets and the calculations had said it must. The emptiness, it turned out, had never been empty. Parker had been right all along. I think there is something deeply restful in that. Not the triumph of it exactly, but the patience. A man looked closely at the sun, saw something no one else was willing to see, and was content to be doubted while the universe slowly confirmed it on its own schedule. The wind had been blowing the entire time, for billions of years, long before anyone gave it a name, long before there was anyone here to name anything at all. Parker did not invent the solar wind, he simply noticed it, and then he was kind enough and stubborn enough to keep believing in it until the rest of us caught up. His idea changed everything about how we picture our place in the solar system. We do not orbit a distant, separate fire. We live inside the sun's atmosphere. The solar wind reaches out so far that it carries the sun's presence past all the planets, forming an enormous bubble around the entire solar system, a region we now call the heliosphere. Everything we know, every world we have ever touched, every signal we have ever sent, sits inside that bubble, bathed in the wind from our star. We are not neighbors of the sun. We are residents within it, living deep inside the gentle outward breath of the fire that made us. And it is worth pausing on just how far that bubble reaches, because the scale of it is hard to hold. The solar wind does not fade away at the edge of the planets. It keeps blowing outward, past Jupiter and Saturn, past the cold and distant worlds at the very rim of the planetary family, on and on through the dark, for billions upon billions of miles. We know this because we have followed it all the way to its edge. Decades ago, we launched a pair of spacecraft called Voyager, and we sent them outward, and they flew on for more than 40 years, crossing distances almost beyond imagining. And only after all that time, more than 11 billion miles from home, did they at last reach the place where the solar wind finally grows tired and thin and gives way to the wind of other stars. That faraway boundary, the true outer shore of the sun's atmosphere, has a name. It is called the heliopause. It is the edge of our star's vast breathing bubble, the last whisper of its wind. So when we say we live inside the sun's atmosphere, we mean it more completely than you might think. Everything you have ever known, every person who has ever lived, every single event in all of human history has happened inside that one enormous, gentle exhale of the sun. A bubble so large that our fastest machines needed half a century just to find its far edge. We do not merely live near our star. We live deep inside it, cradled in its wind, all the way out to the quiet shore where it finally meets the dark. But here is the question that Parker's wind quietly forced upon everyone, once they finally accepted it. If the corona is hot enough to blow a wind across the entire solar system, then just how hot is it? And how did we ever come to know? This is its own small mystery, and a beautiful one. For most of history, no one had any idea that the sun's outer atmosphere was anything other than warm. The first clue came during total eclipses, in those rare moments when the moon slides perfectly across the sun and reveals the faint corona around it. For most of history, those few fleeting minutes of a total eclipse were the only chance anyone had to see the corona at all. The sun's ordinary glare drowns it out completely, washes it from the sky. So when the moon slid perfectly across the sun and the day went suddenly dark, astronomers would travel across oceans and continents, carrying delicate, fragile instruments to remote deserts and mountaintops and tiny islands, all for a window of perhaps 2 or 3 minutes. And in those minutes, with the bright face of the sun hidden at last, the corona would bloom into view, a pale crown of light reaching out in soft streamers and petals, its shape different at every eclipse, shifting quietly with the sun's hidden moods. When astronomers in the 1800s began to study the light of that crown carefully, splitting it into its colors, the way a prism splits sunlight into a rainbow, they found something they could not explain. A bright green line of light, glowing at a color that matched no known substance on Earth. It was a genuine puzzle. Every element, when heated, glows with its own particular set of colors, like a fingerprint. And this green light from the corona matched nothing in any laboratory. So for a time, astronomers did the only thing they could. They assumed it must come from some new element, one that existed only in the sun's atmosphere and nowhere on Earth. They even gave it a name. They called it coronium. Coronium was a ghost, a placeholder for something no one understood, and it haunted the edges of solar science for the better part of 70 years, this strange green light with no source, until finally, around 1940, 2 physicists named Walter Grotrian and Bengt Edlin quietly solved it. The green light, they showed, was not a new element at all. It was iron, ordinary iron, the same metal in a kettle or a key, but iron that had been stripped of many of its electrons, torn apart far more violently than any flame on Earth could ever manage. And here was the staggering part. For iron to lose that many of its electrons, to glow with that particular green light, it would have to be heated to over 1 million degrees. That was the moment we learned the truth. The faint, wispy crown around the sun, the part farthest from its fire, was not merely warm. It was over 1 million degrees, hundreds of times hotter than the bright surface beneath it. The ghost of coronium had been the sun all along, quietly telling us its strangest secret, and it took us 70 years to learn how to listen. So by the time Eugene Parker came along with his wind, the deeper mystery was already sitting there, waiting. We knew the corona was impossibly hot. We knew, thanks to Parker, that its heat was enough to blow a wind across the whole solar system. What we did not know, what we still do not fully know tonight, more than 80 years after Grotrian and Edlin read the green light correctly, is the simplest question of all. Why? Why is the corona that hot in the first place? It is one of the oldest unanswered questions in all of physics, older than spaceflight, older than the computers we used to solve 1,000 harder-seeming problems. And there is one more gift in Parker's story, a small and gentle one before we move on. Many years later, long after the doubt had faded, and the solar wind had become an ordinary fact in every textbook, NASA decided to build the spacecraft we have been quietly waiting to meet. A machine designed to do the one thing no one in Parker's day could have imagined: to fly directly into the sun's outer atmosphere and measure the wind at its source, and perhaps, at last, to learn why that atmosphere burns so impossibly hot. And when it came time to name it, they did something they had never done before in all their history. They named the mission after a living person. They called it the Parker Solar Probe. Eugene Parker was 91 years old when that spacecraft left the Earth. He traveled to Florida to watch it go, and in the early morning, he stood and looked up as the rocket carrying his name and his idea rose into the dark and climbed toward the very star he had spent his whole life trying to understand. The young physicist, no one believed, had lived long enough to watch us reach out and touch the thing he saw first, blown gently outward, all those years ago, in the backward-pointing tails of comets. But the solar wind, and even the ancient riddle of the corona's heat, were only the beginning of what waited out there. Because to truly understand any of it, the machine that bore Parker's name would have to do something almost unthinkable. It would have to survive a journey into the fire itself. That is where we are going next. How do you build something that can fall into a star and live? But there is no hurry. The wind has been blowing for billions of years. It can blow a little longer while you rest. The trouble with the question we just asked is that you cannot answer it from here. You can look at the sun for a lifetime. You can split its light into colors, the way Grotrian and Edlen did, and read its temperature in a strange green line. You can study its warmth, photograph its outer atmosphere during an eclipse, measure the wind as it arrives at the Earth. People did exactly all of that for generations, and they learned a great deal. But there is a limit to what looking from a distance can ever tell you. To truly understand why the corona burns hundreds of times hotter than the surface beneath it, you would need to go there. You would need to put something inside that million-degree crown and let it feel the heat directly, sample the wind at its source, and send word back. And for almost the entire history of spaceflight, that was simply impossible. The idea of flying a machine into the sun's atmosphere belonged to the same shelf as flying one into the heart of a thunderstorm made of fire. It was a lovely thought. It was not an engineering plan. And yet, remarkably, the dream is very old. In 1958, the very same year that Eugene Parker published his quiet, doubted paper about the solar wind, a group of American scientists drew up a wish list of the great missions they hoped to fly one day. And near the top of that list, even then, at the very dawn of the space age, when we had managed to put only the smallest satellites into orbit around our own planet, someone wrote down the boldest destination of all, a probe to the sun, to fly a machine to the nearest star and study it from inside. Think of that. In the same year, the same idea arrived from two directions at once. One man imagined the wind pouring out of the sun, and another group imagined sailing a small craft up the wind to its source. Both ideas were far ahead of their time. Both would have to wait. Parker waited only a few years to be proven right. The mission to the sun would have to wait far longer. 60 years, as it turned out. The reason for that long wait was not a lack of will, and not a lack of dreaming. It was that the materials did not exist yet. We had to wait for the science of heat shields to grow up. We had to learn how to make something light enough to launch, and strong enough to stand inside a furnace, and clever enough to keep its own delicate heart cool while its outer face glowed. None of that could be rushed. It took half a century of patient progress in materials and engineering, 60 years of small steps, before the dream written down in 1958 could finally be built. And then, at last, on a humid morning in Florida in August of 2018, it was ready. The Parker Solar Probe rose from its launch pad in the dark before dawn and began its journey toward the closest, brightest, most familiar star in our sky, the one we almost never think about as a place you could travel to at all. It very nearly did not go that morning. The day before, the rocket had stood ready on the pad, fueled and counting down, and in the final minutes, with the launch only seconds away, a warning flickered somewhere in the system, and the attempt was quietly called off. Everyone went home to wait another day. There is only a narrow window each morning when the path to the sun lines up just so, a matter of minutes, and if you miss it, you simply try again tomorrow. So they came back in the small hours before dawn, and they counted down once more. And this time, in the dark, the rocket lit the sky and climbed away, carrying the little probe up and out, beginning a fall toward the sun that would take 6 long years to complete. Somewhere among the watchers, an old man with the spacecraft's name was looking up. The spacecraft it carried is surprisingly small. We tend to imagine the machines we send into space as enormous, and some of them are. But this one is roughly the size of a small car. You could park it in a single space and have room to walk around it. And tucked into that modest body is a small, careful collection of instruments, each one built for a single quiet task. Some are designed to feel the sun's magnetic field directly, to sense the invisible lines we talked about earlier as the probe passes through them. Others are built to catch and count the actual particles of the solar wind, to taste the stream Parker imagined, one grain of plasma at a time, and one, looking out sideways from the safety of the shadow, is a camera meant to photograph the corona from inside it, to take pictures of the wind from within the wind itself. If you could stand beside the Parker Solar Probe, the first thing you would notice is a broad, flat disc fixed to one side of it, a little under 8 feet across. That disc is the heat shield, and it is the entire reason the mission can exist. It is only about 4.5 inches thick, not much more than the width of your hand, but those few inches are doing something almost unimaginable. They stand between the fragile body of the spacecraft and the full fury of the sun. The shield is made of carbon, 2 thin faces of a carbon composite, the same family of materials used in the most advanced aircraft and race cars, wrapped around a core of carbon foam that is almost entirely empty space. It is light enough to lift in your arms, lighter than you would ever believe something so tough could be. And the side that faces the sun is painted a careful, brilliant white, a specially made coating designed to do one simple thing: to reflect away as much of the sun's light as it possibly can, throwing the heat back before it can ever soak in. A white shield turned always toward the fire, bouncing the worst of it away. And for all that it can do, the shield is astonishingly light. You might imagine that standing against a star would require something massive, a great slab of metal. It is the opposite. The whole shield weighs only about 160 pounds, less than a single grown person, because its heart is not solid at all. That carbon foam core is almost entirely empty space, something like 97 parts air to 3 parts material, a froth of carbon so full of tiny gaps that it is mostly nothing. And it turns out that nothing is one of the finest insulators there is. The emptiness inside the shield is part of what keeps the heat from crossing it. A few inches of mostly air, held between two thin faces of carbon, standing calmly between a delicate machine and the full blaze of the sun. There is something almost gentle in that the thing protecting the probe from a star is, in large part, simply empty space, carefully arranged. Here is the part that I find quietly astonishing and worth slowing down for. As the spacecraft sweeps through the sun's outer atmosphere, the front face of that shield climbs toward roughly 2,500 degrees Fahrenheit. That is around 1,400 degrees Celsius, hot enough to melt steel, hot enough to glow a dull, angry red. The face of the shield bakes in a heat that has no equal anywhere in our ordinary experience. And just behind it, in the shadow the shield casts, the instruments sit at around room temperature. The temperature of a comfortable afternoon. The temperature of the room you are lying in right now. Sit with that for a moment, because it is one of the gentlest, strangest facts in all of spaceflight. The difference between the front of that shield and the delicate machinery a few feet behind it is the difference between the inside of a furnace and a quiet living room. The shield does not fight the heat exactly. It does something simpler and more graceful. It blocks the sun, and it casts a cool shadow. And inside that shadow, the whole mission lives. Everything the spacecraft needs to do, all of its seeing and feeling and counting and remembering, happens in a small pocket of calm, tucked behind a few inches of carbon, in the one shaded place anywhere near the sun. The probe carries its own little patch of shade with it into the fire, the way you might hold a small umbrella against a downpour, and lives its entire close life beneath it. Of course, a shadow only protects you if you stay inside it. And so the entire spacecraft is built to keep that shield pointed at the sun at all times, with a kind of patient, instinctive vigilance. Tiny sensors are placed around the edges of the body, watching for the very first touch of direct sunlight creeping past the rim of the shield. If they ever feel that light, even a sliver of it, the spacecraft gently turns itself, on its own, without waiting to be told, tucking back fully into shade before any harm is done. It is always making these small, quiet corrections, always nudging itself back into its own shadow, the way a sleeper turns away from a window when the morning sun begins to fall across the bed. It is a lonely sort of vigilance when you think about it. No one is steering. There is no one aboard, and no one near enough to help. The little machine simply watches its own edges, hour after hour, year after year, quietly keeping itself in shade, the way a sleeping creature shifts and settles without ever waking. All that careful attention, all that constant, patient self-protection, carried out in silence, millions of miles from the nearest hand that built it. Even its wings are careful. The solar panels that gather sunlight for power cannot simply spread wide near the sun, the way they would anywhere else, because near the sun that much light would cook them. So most of each panel is folded away behind the shield, and only thin slivers are allowed to peek out into the light, just enough to keep the spacecraft powered. And even those slivers are cooled quietly by water flowing through them, carrying the heat away so they do not melt. Every single system is a small, thoughtful answer to the same question, asked over and over. How do we stay cool, this close to the fire? But building a machine that could survive the sun was only half of the challenge. The other half was getting it there at all. And this is where the story turns genuinely surprising, because falling into the sun is far harder than it sounds. It is the reason that launch had to be one of the most powerful ever flown. Most of us carry a quiet assumption that the sun is a kind of drain, that its gravity is so enormous, anything that drifts loose will simply slide toward it and fall in. It feels intuitive. The truth is almost the opposite. Reaching the sun is one of the most difficult destinations in the entire solar system. So difficult that, measured in the energy required, it is actually much harder to fall into the sun than it is to leave the solar system altogether and sail off into the stars. There is a striking way that the engineers sometimes put it. It takes roughly 55 times more energy to reach the sun than it does to reach Mars. 55 times. The nearest star, the thing at the very center of everything, is one of the hardest places we can possibly go. The reason is motion. The Earth and everything on it, and everything launched from it, is not sitting still beside the sun. We are racing around it, sideways, at about 67,000 miles per hour. We have always been moving like that, which is exactly why we never fall in. Our enormous sideways speed is constantly carrying us past the sun, rather than into it, the same way a stone whirled on a string circles your hand instead of striking it. Imagine standing at the edge of a child's merry-go-round as it spins and trying to drop a small ball directly onto the pole at the very center. You cannot simply let the ball go because your hand and the ball in it are already sweeping sideways with the spin. Released, the ball flies off past the center, carried by the sideways motion it inherited from you. To actually drop it onto the pole, you would first have to somehow cancel all of that sideways speed. And that is exactly the problem with reaching the sun. To fall inward, the probe has to shed most of the 67,000 miles per hour of sideways motion it was born with, simply by being launched from a moving Earth. And shedding that much speed takes a staggering amount of energy, far more than any rocket we have could ever provide on its own. Which is why the Parker Solar Probe does not fly to the sun in a straight line. It cannot. Instead, it falls inward slowly, patiently, over years, by borrowing help from another world. That world is Venus. 7 separate times across its journey, the spacecraft swings close past Venus, and each time, it uses the planet's gravity to reshape its own path. This is a technique called a gravity assist, and it is one of the most elegant ideas in all of space travel. As the probe passes the planet, Venus's gravity reaches out and tugs on it, and in that brief encounter, the two trade a little energy between them. The spacecraft gives up some of its precious sideways speed, handing it quietly to Venus, and in return, its orbit tightens. Its closest approach to the sun drops a little nearer. Venus, being unimaginably more massive, barely notices the exchange. It is a little like a small boat slipping past a great moving ship and catching a change in its wake. The boat is nudged onto a new course. The ship sails on, entirely unbothered, and the passes by Venus gave us an unexpected gift along the way. On one of those swings past the planet, the spacecraft's camera happened to be looking toward Venus's night side, and it saw something no one had planned for. Venus is wrapped in a thick, permanent shroud of cloud, so dense that its surface is normally hidden completely from view. But in that image, faintly, the camera saw straight through the clouds to the ground below, glowing softly with its own heat, revealing the dim shapes of the Venusian landscape, its highlands and lowlands, lit from within like an ember seen through smoke. It was a small accident of the journey, a side glance on the way to somewhere else. The probe was only using Venus to bend its path toward the sun. And in passing, almost by chance, it gave us a rare, quiet look at the hidden face of a neighboring world. And then it does it again and again. The first of those 7 passes came just weeks after launch, in the autumn of 2018. The last of them came 6 years later, in the autumn of 2024, the final gentle push that would set up the deepest dive of the whole mission. In between, year after year, the spacecraft looped back out, swung past Venus, shed a little more of its sideways motion, and fell a little closer to the star. Each pass drew the loop tighter, like water circling slowly toward the center of a basin. It was not a dive. It was a long, unhurried spiral inward, measured not in minutes, but in years, the most patient approach imaginable to the most extreme place we have ever tried to reach. It did not reach its closest distance all at once, either. That too came slowly. On its earliest passes, the probe swept by the sun several times farther out than it would in the end, already closer than anything before it, but still keeping a careful distance. And then, with each loop past Venus, the closest point of its orbit edged nearer, a little closer this year, a little closer the next. Across 24 long, patient orbits, the spacecraft drew the bottom of its loop steadily inward, from many millions of miles out, down and down, until at last it would skim just 3.8 million miles above the surface. It is a strange kind of courage to approach something so dangerous so slowly, testing the heat a little more each time, trusting the shield a little further with every pass, never rushing, always returning, drawing nearer to the fire by careful degrees over the better part of a decade. There is something almost restful about the geometry of it. We so often picture space travel as fire and thrust and speed and noise. But the journey to the sun was mostly a matter of letting go, gently and repeatedly, of the very motion that keeps us safe, until at last the little machine was close enough to touch what it came for. 6 years of falling, 6 years of patience, the same patience Parker himself had shown, now built into the path of the spacecraft that carried his name. And as the loops tightened, something else happened, almost as a side effect. The spacecraft began to move faster than anything humans had ever built. This is the strange arithmetic of falling toward a star. The closer you fall, the harder the sun's gravity pulls, and the faster you go. With every spiral inward, the probe whipped around the sun at the bottom of its loop at a greater speed than the time before. In fact, on its very first close pass, only a few months after launch, it had already broken a record that had stood for more than 40 years. Back in the 1970s, a pair of probes called Helios had flown closer to the sun, and faster than anything before them, and their record had gone unbroken for decades. The Parker Solar Probe passed it on its first attempt, and then simply kept going, outrunning every spacecraft, every probe, every machine that had ever come before it, by a wider and wider margin with each loop. And it was not finished. The very fastest moment of its entire mission, the closest it would ever come, the deepest plunge into the fire, was still ahead of it. So here we are, at the bottom of the long spiral, inside the crown of light, in the place the whole journey was built to reach. And now we can finally sit with the question that has been waiting for us since the very beginning of the night. Why is it so hot here? Let me say something honest before we go any further, because honesty is the whole point of a place like this. We are about to walk through the leading ideas scientists have for what heats the corona, but none of them is yet the answer. This is one of the oldest unsolved problems in all of physics. older than spaceflight itself, and it is still quietly open. We are closer than we have ever been. We are not at the end. So think of what follows not as a solution being handed to you, but as a small group of patient people standing around something strange and beautiful, turning it over in their hands, saying, maybe it is this, or maybe it is this. We are not certain yet. And that uncertainty is not a flaw in the story. It is the most truthful and most human part of it. Let me show you what it actually looks like in here first, before we ask why it burns. The corona is not a smooth, featureless haze. It is a landscape, vast and slow and strange. Great arcs of glowing plasma rise from the surface and curve back down again, tracing the loops of the magnetic field, some of them tall enough to swallow the Earth many times over, standing like luminous bridges in the light. In other places, enormous bright structures called streamers reach far out into space. The long petals you can see in photographs of an eclipse, pointed and feathered. And sometimes great ribbons of cooler, denser plasma hang suspended above the surface, held up by invisible magnetism, glowing softly against the brighter background. It is a quiet, towering, ever-shifting architecture of light and magnetism, all of it moving far too slowly for the eye to follow, all of it hotter than anything we can make. This is the place the little machine flew into. This is the crown. To feel just how strange the puzzle is, let us take a slow imaginary climb, upward, away from the surface of the sun, and watch what the temperature does as we go. We begin at the surface, the bright golden face we can see, the photosphere. It sits at around 5,500 degrees, hot beyond anything on Earth, but a number we can at least hold in our minds. Now we rise. Just above the surface lies a thin layer called the chromosphere, a soft reddish region you can sometimes glimpse during an eclipse as a rosy rim around the dark moon. As we climb through it, something gentle and unexpected happens. The temperature begins to fall. We are moving away from the heat, after all, just like stepping back from the campfire, and the air grows cooler, down to a few thousand degrees. So far, everything behaves exactly as your intuition says it should. And then we reach a place where intuition simply breaks. Just above the chromosphere lies an astonishingly thin shell, a layer so slender it would be easy to miss, called the transition region. And as we pass through it, in a span thinner than you would ever believe, the temperature does not gently rise, it leaps. It vaults upward, in the space of just a short distance, from a few thousand degrees to over 1,000,000, a 100-fold jump, almost like a wall, as though we had climbed a quiet staircase and stepped through a door into a furnace. One moment we are in cool, thin air, moving away from the fire. The next, we are in a 1,000,000-degree atmosphere that stretches out for millions of miles. There is no slow warming. There is a sudden, almost violent leap packed into a razor-thin shell, and no one fully understands why it is there or how it is so abrupt. That is the coronal heating problem, made visible. A cool layer, and then a thin wall, and then beyond it, a crown hundreds of times hotter than the surface that supposedly feeds it. And to understand why that should trouble us so deeply, we have to return for a moment to that ordinary fact about heat, the one from the campfire. Heat flows from hot things to cooler things, always. A warm cup left on a table cools toward the temperature of the room. The room never spontaneously pours its warmth back into the cup to make it hotter. This is one of the deepest rules in nature, and nothing we have ever observed truly breaks it. Now hold that beside what we just climbed through. The surface sits at 5,500 degrees. The atmosphere above it blazes at more than 1,000,000. If the surface were simply heating the air above it, the way a campfire heats the night, then that air could never become hotter than the surface itself. Heat does not flow uphill. The cooler surface cannot, by any ordinary means, be the thing making the corona so much hotter than itself. And yet the corona is hotter, which tells us something quietly profound. The heat up there is not arriving by ordinary means at all. Some other channel is carrying energy past the surface, past the cool layers, and dumping it into the atmosphere above, a hidden pipeline that skips the rules we know. And for most of a century, the search for the coronal heating problem has really been a search for that hidden pipeline. What is it? Where does it run? How does it work? And here is a subtle thing worth understanding, because it sharpens the mystery rather than softening it. The puzzle is not that the sun lacks the energy to heat its corona. The sun has energy beyond all reckoning. In fact, the amount needed to keep the corona glowing at 1,000,000 degrees is only a tiny sliver of the sun's total output, a faint fraction of a fraction of all the light and heat it pours out every second. There is more than enough energy to spare. The mystery is not the supply, it is the delivery. It is how that energy gets carried, untouched, past the cooler surface and the cool layers above it, and then released all at once, high up in the thin atmosphere where it has no business being. It is not a question of how much, it is a question of how. And that, somehow, is the harder question. The prime suspect, the thing nearly everyone agrees must be involved, is invisible. It is the sun's magnetic field. We do not usually think of the sun as magnetic, but it is, intensely so. Beneath its surface, vast rivers of churning plasma generate magnetism on a scale that dwarfs anything on Earth. And because the corona is made of plasma, of charged particles, it does not simply float freely. It is gripped by that magnetism, threaded through with magnetic field lines, shaped and held and sculpted by them. Those glowing loops and arcs you sometimes see in images of the sun are plasma, tracing out the invisible magnetic structure the way iron filings arrange themselves into curves around a magnet on a child's desk. The corona is not really a cloud of gas. It is a magnetic place, a landscape of invisible lines, and the energy that heats it almost certainly travels in along those lines. The question is how. And here the patient people around the strange object begin to offer their different answers. The first idea is about waves. Decades ago, a Swedish physicist named Hannes Alfvén realized that a magnetic field threaded through plasma can carry waves, the same way a guitar string carries a note when you pluck it. Tug on a magnetic field line, and a ripple travels along it. Alfvén's insight into how plasma and magnetism move together was so fundamental that it eventually earned him the Nobel Prize, and it opened up an entire field of physics. The churning surface of the sun, he understood, is constantly tugging, constantly jostling the bases of these magnetic lines, and so waves are forever traveling upward along them, out of the surface and into the corona. These are now called Alfvén waves, after the man who imagined them. And the idea is that as these waves climb into the thin upper atmosphere, they break, the way ocean waves break as they reach the shallows of a shore, releasing their energy into the plasma around them and warming it. Countless waves rising endlessly along the magnetic field, each one carrying a small parcel of energy up from the surface and spending it in the corona as heat. It is a beautiful picture, a star humming with invisible waves, warming its own crown with music it cannot stop playing. The second idea belongs fittingly to Eugene Parker himself. The same man who gave us the solar wind spent much of his life turning over the heating problem too, and he offered an idea of his own. To understand it, picture first the largest eruptions the sun can make, the great solar flares we can watch from Earth. A single large flare releases an almost unimaginable amount of energy, as much as billions of explosions, a burst of light and heat that can be seen across the entire solar system. Parker's idea was that the same kind of event might be happening on a tiny scale, all the time, everywhere. He suggested that the sun's magnetic field, constantly shoved around by the motion of the surface, gets tangled. Field lines wind around one another, twist, knot, store up tension like a rubber band wound far too tight. And every so often, when the strain becomes too much, the tangled lines snap and rearrange themselves into a simpler shape, releasing their stored energy in a sudden small burst. This snapping and rejoining of magnetic field lines is called magnetic reconnection, and on a grand scale, it produces those enormous visible flares. Parker's idea was that on a tiny scale, it might be happening constantly, in countless places at once. Not a few great flares, but millions upon millions of almost invisibly small ones, each one a faint pop of magnetic energy. He called these tiny events nanoflares. Picture that for a moment, slowly. The entire surface of the sun, gently crackling with countless tiny explosions, each one far too small and too quick for us to catch on its own, but all of them together pouring a steady river of heat up into the corona. Each one almost nothing, all of them together perhaps, enough to keep a 1,000,000-degree crown alight, a star warming its own atmosphere not with one great fire, but with an endless, invisible shimmer of tiny ones. And this snapping and rejoining of magnetic field lines, this magnetic reconnection, is not something exotic that happens only on the sun. It happens far closer to home. It happens high above our own heads when the sun's magnetic field meets the Earth's, and the lines break and reconnect and fling energy down toward the poles, lighting the auroras we will speak of later. Now, you might be wondering which of these is the real answer, the waves or the tiny flares, and the gentle truth is that they may not be rivals at all. Both ideas are really about the same thing: energy traveling out of the sun along its magnetic field and spending itself as heat in the atmosphere. One imagines that energy arriving as smooth, rising waves. The other imagines it arriving as countless small bursts. And in truth, they even blur into one another, because a breaking wave and a snapping field line are not so different deep down. The honest current view is that the corona is probably heated by some blend of both, in proportions that change from place to place across the sun, and that we still cannot fully measure. The patient people are still standing around the strange object, and the most truthful thing they can say is that it seems to be some of this and some of this, and they would dearly love to know how much of each. Which is exactly why we built a machine to go and listen. Not to settle the argument from a distance, but to fly into the corona and feel directly what the magnetic field was actually doing in there. And when the Parker Solar Probe finally crossed into that atmosphere and began to send its measurements home, it found something no one had quite expected. It found that the magnetic field, this close to the sun, was not smooth and orderly at all. It was full of sudden, sharp reversals. Again and again, as the probe flew through the wind, the magnetic field would abruptly fold back on itself, bending into a tight S-shaped kink, pointing briefly backward before snapping forward again. Scientists called these features switchbacks, after the sharp doubling turns of a mountain road, and each time the spacecraft passed through one, it measured a sudden jump in the speed of the solar wind, a little surge of plasma rushing outward, as if the folded field had given the wind a quick, hard shove. This was the kind of discovery that quietly excites people, because a switchback is not just a curiosity. It is a fingerprint. Something down near the surface is violently kinking the magnetic field and flinging these folds outward. And whatever is doing that is exactly the sort of process, magnetic, energetic, sudden, that could also be heating the corona and driving the wind. The switchbacks were a clue left at the scene, a sign of the hidden machinery at work. It is a little like finding the crack of an invisible whip. Somewhere, something is snapping the magnetic field hard enough to send these folds racing outward through the wind, one after another, and reading them is like hearing the sound and trying to picture the hand that made it. But here too, the honesty matters. Scientists are still genuinely divided on how the switchbacks come to be. Some think they are made right down at the surface, born in those violent little reconnection events near the funnels and flung outward already folded. Others think the field leaves the sun smoother than that and only crumples into switchbacks later, kinked and tangled by the turbulence of the wind as it travels. It may even be some of both. The folds are real, and we have measured them carefully. Exactly where and how they are born is still being argued over gently in papers and at conferences, which is simply what an open question looks like while it is being answered. The probe helped with another old puzzle too, one hiding inside the wind itself, for the solar wind is not all one thing. There is a fast wind racing out at the higher speeds, and there is a slow wind drifting out at perhaps half that pace, and the two behave quite differently. The fast wind, we have come to understand, pours out mainly through those open doorways, the coronal holes, gushing freely into space. But the slow wind has long been more mysterious. By flying through both kinds of wind close to their source, sampling them directly while they were still young, the probe has begun to help untangle where each one is born. It has not closed that question either, but it has brought us nearer and given us cleaner clues, which near the sun is worth a great deal. The probe did not arrive and announce the answer. It did something better and more honest. It showed us that the place was even richer and stranger than we had guessed, and it handed us new clues to follow, and a clearer idea of where the wind, and perhaps its heat, truly begins. And there was one more thing it found as it fell closer, something quieter, almost tender. The solar system is dusty. It always has been. Drifting between the planets are countless tiny grains, fragments of ancient comets and shattered asteroids, some of them older than the Earth itself, older than any world. This faint haze of ancient dust fills the inner solar system, so fine and so spread out that on a dark, clear night, you can sometimes see sunlight glowing softly through it, a pale cone of light leaning up from the horizon just after sunset or before dawn. It has a lovely old name. We call it the zodiacal light. That dust has a long and humble history of its own. It is the debris of the solar system, the leftover crumbs of creation. Some of it is shed by comets as they swing past the sun, and their ices boil away, leaving trails of fine grains behind them. Some of it is the powder of ancient collisions between asteroids. worlds that shattered against one another long ago, ground down over the ages into a fine, drifting haze. For billions of years, this dust has been circling the sun, slowly, patiently, far too sparse to see except as that faint cone of light on a dark night. It is, in a sense, the ash of the solar system's own long history, the scattered remains of everything that has broken and worn away out there since the beginning. And it fills nearly all the space between the planets, everywhere we have ever looked. Everywhere, that is, except for one place. For a long time, going back the better part of a century, scientists suspected that very close to the sun, this dust must simply cease to exist, that somewhere near the star, the heat would become so intense that the grains would not merely melt, but vaporize outright, turning straight from solid dust into gas, leaving behind a region swept perfectly clean. As the Parker solar probe fell inward, past where any machine had ever traveled, its camera watched the dust around it slowly thin, and then, approaching the sun, begin to disappear, exactly as predicted, the ancient grains quietly vaporizing in the heat, leaving the first real evidence of that pristine, swept, clean void wrapped around the star. A prediction made by people who would never see it, confirmed at last by a small machine falling through the very place they had imagined. Think of what that means softly as you lie there. There is a region close to the sun where the dust of the early solar system, grains that have drifted untouched for billions of years, simply ends. A clearing in the haze, the oldest material we have, gently erased by the warmth of the star it has circled since the beginning. And until a few years ago, no one had ever seen it. We had only imagined it might be there. And then a small machine wrapped in carbon fell close enough to find that the imagining was true. This is what the probe gave us. Not a tidy answer to the great question, but the texture of the place itself. A thin wall where the temperature leaps 100-fold. A magnetic field that folds and snaps. A wind shoved outward in sudden surges, traced back toward the funnels where it is born. A swept clean clearing where the oldest dust quietly ends. Each one a piece of the puzzle, none of them the whole of it. The corona kept its deepest secret even as it let the machine pass through. And somehow that feels right. Some things are meant to be approached slowly, over generations, a little more understood with each careful visit. There is a kind of patience required to live with a question like this, and the people who study the sun have it in abundance. They do not expect a single answer to arrive in a single lifetime. They add a careful measurement here, a cleaner observation there, narrowing the possibilities slowly, comfortable with the long, unhurried pace of real understanding. It is not so different in the end from the way the probe itself approached the sun, slowly, carefully, a little closer each time. Let's leave the fire for a little while and come home, because while the spacecraft was falling toward the sun, there were people here on this small blue world who had spent their whole careers waiting for what was about to happen. Some of them had spent their whole lives on it, and to understand the weight of it, we have to step away from the plasma and the magnetic fields and stand for a moment with them in the quiet, in a low-lit room in a place called Laurel in Maryland, where the mission was watched over. It was Christmas Eve 2024. Across much of the world, it was the stillest night of the year, the night people come home, the night houses fill with the soft noise of family, and then slowly fall quiet as everyone drifts off to sleep. Children listening for footsteps on the roof, lights left low, the whole hemisphere settling into its longest, gentlest pause. And on that same night, a small machine the size of a car was making the closest approach to the sun that anything built by human hands has ever made. At its closest, the Parker Solar Probe passed about 3.8 million miles above the surface of the sun. Now, 3.8 million miles sounds impossibly far, the kind of distance that means nothing to the human mind. So let me shrink it down for you. Imagine the entire distance from the sun to the Earth, all 93 million miles of it, drawn out as a single football field. The sun resting on one goal line, the Earth on the other, 100 yards of empty space between them. On that field, at its closest approach, the probe was about 4 yards from the sun. 4 yards on a 100-yard field. After a journey of 6 years and 7 loops past Venus, it had crossed almost the entire distance to the star and was skimming just above it. And it was moving faster than anything humans have ever made, about 430,000 miles per hour. That number is just as hard to feel, so here is a way to hold it. At that speed, you could cross the whole of the United States, coast to coast, in roughly 20 seconds. A single slow breath, and you would be on the other side of a continent. That is how fast the probe was traveling as it rounded the sun. The fastest human-made object in all of history, reaching its greatest speed at the closest point of its deepest dive, exactly as the long spiral had always been building toward. At 430,000 miles per hour, the probe could circle the entire Earth, all the way around, in just a few minutes. It could travel from here to the moon, that long voyage that once took our astronauts 3 days, in something like half an hour. It is moving so fast that if it were skimming low over a city, it would cross from one side of a continent to the other before you could finish a slow, sleepy thought. And it reaches that speed not because of any engine roaring inside it, for it has no great engine, but simply from falling, pulled faster and faster by the gravity of the sun. The way anything gathers speed as it drops, it is, in a sense, the fastest falling thing in the history of the world. And the light it flew through that close is almost beyond imagining. We are used to the sun as it appears from here, bright enough to make us squint, warm on the skin on a summer afternoon. At its closest approach, the front of that little shield was bathed in sunlight, roughly 475 times more intense than anything we ever feel on Earth. 475 times. A blaze so fierce that the entire purpose of that 4.5 inches of white carbon was to stand in front of it and simply hold it back, glowing red on its face, while the machine behind it stayed cool. This was the moment everything had been built for, the deepest, brightest, fastest point of the whole mission, and try gently to picture where it was. Not in clean, empty space, but down inside the sun's own atmosphere, surrounded on every side by the corona, that million-degree crown we spent so long getting to know. Plasma streaming past it at incomprehensible speeds, light pressing in from all directions at once, fierce beyond anything the Earth has ever felt. The magnetic field folding and snapping around it in those switchbacks, the very wind it had come to study rushing by. And in the middle of all of that, the small machine, calm behind its glowing shield, doing exactly what it was built to do. It was not a violent scene from the probe's point of view. It was simply work, steady, patient, careful work, carried out in the most extreme place any human creation has ever been, while the world that made it slept. and it was the moment no one on Earth could watch. Because to make that pass, the spacecraft had to do what it had always done near the sun. It turned its shield to face the star, tucking every instrument, every antenna, every fragile part of itself into the cool shadow behind that carbon. And with the shield pointed at the sun, there was no way for it to point an antenna back at the Earth. It could not call home. For the most important hours of its entire mission, the probe would be completely silent, out of reach, entirely on its own. For about 36 hours, there would be nothing. No signal, no data, no way for anyone on Earth to know what was happening or to help if something went wrong. The team that had spent years, in some cases decades, building this machine could do absolutely nothing in those hours but wait. Everything they could do, they had already done. Every line of instruction was already loaded into the spacecraft's memory. Every decision it might need to make already taught to it in advance. From here, the probe would have to look after itself. It would have to sense the edge of the sunlight, turn to stay in its own shadow, watch its own temperatures, make its own small decisions in the dark beside the star, with no one to tell it what to do and no way to reach it if it faltered. And it truly was alone. There was no way to fly it by hand, no joystick on Earth, no command that could reach it in time. Even if someone had seen a problem developing, the distance was so great and the silence so complete that any instruction would have arrived far too late to matter. So the spacecraft had been built to need no one. Deep in its design were systems whose only job was to watch over the probe itself, to notice the first hint of trouble, a temperature creeping too high, the shield drifting a fraction off the sun, and to fix it instantly on its own, without asking permission, without waiting for help that could not come. The engineers had poured years into teaching it how to save its own life, and now, in the silence, they had to simply believe that they had taught it well enough. There is no harder kind of trust than that, the trust you place in something once it is finally beyond your reach. There is something almost parental in that. You build a thing with your own hands. You give it everything you know. You teach it, as carefully as you can, how to take care of itself. And then there comes a moment when you have to let it go somewhere you cannot follow and simply trust that it will remember what you taught it. Every parent knows some version of that moment. The front door closing, the car pulling away, the held breath of letting something you love go on without you. The people in Laurel had built the probe to be capable of exactly this, to take care of itself in the one place none of them could ever reach. And now, on Christmas Eve, they had to find out if their trust had been well placed. So they waited. On Christmas Eve and through Christmas Day, while the rest of the world unwrapped gifts and shared meals and dozed by the light of the tree, a small group of engineers kept a quiet vigil over a silence millions of miles away. They knew from the careful mathematics of the orbit the exact moment the spacecraft should have reached its closest point. They could mark it on a clock, but knowing where it should be is not the same as knowing it is all right. They knew the probe had reached the fire. They did not yet know if it had come through, and the strangeness of that waiting is worth feeling. All around them, the world was warm and bright and full of the season. Trees lit in living rooms, tables crowded with family. The soft, ordinary comforts of the holiday repeated in a billion homes, and a small group of people sat apart from all of it in a quiet room, their minds fixed on a single point of light millions of miles away, inside a star, where the warmest, brightest, most extreme thing humans had ever touched was either surviving or not, and there was no way yet to know which. The whole gentle, glowing earth on one side, a machine in the fire on the other, and these few people holding both in their hearts at once, waiting for a sign. The plan was simple, almost touchingly so. The spacecraft had been told that once it was safely past the worst of the heat, once it had come back around and could finally turn an antenna toward home, it should send the simplest possible message. Not data, not science, not pages of readings, just a single tone, a plain little signal that meant only one thing: I am here, I am all right. They called it the beacon tone, and everyone was waiting to hear it. It came late on the 26th of December, after the long silence, after Christmas had come and gone with no word. The spacecraft finally turned its antenna back toward home and sent its small signal out into the dark. And here is a detail worth resting on. Even traveling at the speed of light, the fastest anything can possibly go, that little tone took about 8 minutes to cross the gulf between the sun and the earth. 8 minutes, racing through empty space, before it reached a listening dish on the ground. The team could not even hear it the instant it was sent. They had to wait those final minutes too, while the message that the machine was alive was already on its way, already true, but not yet arrived. And then it came, a single, clear tone. The beacon. The machine was alive. It had flown closer to the sun than anything in history, through more than 1 million degrees of heat, through sunlight nearly 500 times fiercer than we ever feel, at 430,000 miles an hour, and it had come through whole. Its shield had held, its instruments were cool and steady in their pocket of shade, and it was already holding, safe in its memory, the record of what it had gathered in the fire, waiting to send it home in the days that followed. I want you to feel the shape of that moment, because it is the heart of the whole night. It was not loud. There were no cheering crowds, no fireworks, just a small group of tired people in a quiet room in Maryland, 2 days after Christmas, watching a faint tone arrive from beside a star and letting out a breath they had been holding since Christmas Eve. Relief settling slowly through a room, the quiet certainty that the thing they had made and taught and let go of had done the impossible thing they had built it for and had lived to tell them about it. Some of them surely thought of Eugene Parker in that moment, the man whose name was painted on the side of the machine and who had once waited years of his own to learn that he had been right. And in that moment, something far larger than a single mission quietly came true. Remember that the dream of flying to the sun had been written down more than 60 years before, back when we could barely reach orbit, a destination so bold it had to wait most of a lifetime for the world to grow capable of it. Generations of scientists had carried that dream forward, many of them retiring, some of them passing away, long before it could be built. And now, on a quiet Christmas, a small machine had not only reached the sun, but flown into it and survived again and again, doing the very thing that wish list had imagined when the people who wrote it were young. A dream older than most of the people in that room had finally fully come true. The waiting in that lab was only the last few hours of a waiting that had lasted across whole careers. The probe was unharmed. The shield had held. The little pocket of room temperature calm had stayed calm, even 4 yards from the sun on the field we imagined, even in light 400 times fiercer than noon. And tucked safely inside, it was a record of what the corona had been like in there, at the closest point any human creation has ever reached, waiting patiently to be sent home. So after all of that, the 60 years of dreaming, the carbon shield, the 6-year spiral, the Christmas Eve silence, the beacon tone, after flying a machine closer to a star than anyone in history, again and again, did we solve it? Did we finally learn why the corona burns hundreds of times hotter than the surface beneath it? Let me be honest with you, the way I promised I would be at the start, because the honest answer is the more beautiful one anyway. We are closer than we have ever been, and it is still not fully solved. But before we sit with what remains unknown, let me tell you something the probe did achieve, something genuinely historic, because it deserves to be marked. For all our talk of flying into the sun's atmosphere, there was a real question of where exactly that atmosphere even ends. Where does the sun stop and the solar wind truly begin? It turns out there is a real boundary out there, an invisible line called the Alfvén surface, named once again for that same Swedish physicist. Inside it, the plasma is still bound to the sun, still part of its atmosphere, still ruled by the star's magnetic grip. Outside it, the plasma has broken free and become the wind, racing away forever. And in 2021, the Parker solar probe crossed that line. For the first time in all of history, a machine from Earth passed inside the true edge of the sun's atmosphere and flew within the corona itself. We did not just approach the sun. We entered it. We can say now, plainly and truthfully, that we have touched a star. And the moment it happened was stranger and gentler than anyone expected. When the probe first crossed that boundary, back in the spring of 2021, it did not pass through a clean, sharp line, like stepping through a doorway. The edge of the sun's atmosphere turned out to be uneven, wrinkled, rising and dipping like the surface of a hilly landscape. So the spacecraft crossed in, and then back out, and then in again, dipping below the boundary and rising above it several times over, as though wading into the shallows of a sea, the water lapping up around its ankles and then receding. For those scattered minutes and hours, it was truly inside the sun, surrounded by the star's own atmosphere, the first thing from Earth ever to be so. And then it rose back out into the wind, carrying the knowledge that the edge of a star is not a wall at all, but a soft, shifting, living shore. That alone would have been enough to call the mission a triumph. But it kept going, and it kept teaching us. Remember those two ideas we sat with earlier, the rising magnetic waves and the countless tiny flares? By flying directly through the wind near its source, the spacecraft was able to measure, for the first time, just how much energy those magnetic waves are actually carrying as they climb away from the sun. And the answer turned out to be a great deal. Enough, it seems, to do real work, to genuinely help heat the plasma and push the wind outward. The switchbacks, those sharp folds in the magnetic field, point in the same direction, toward a corona alive with magnetic energy rippling up from below. So the evidence has leaned, in recent years, toward the waves playing a powerful role. But that does not mean the tiny flares are wrong. Both can be true at once, in different places, in different amounts. The picture that is emerging is not a single tidy cause, but a collaboration, a star heating its own atmosphere through more than one process at the same time, the balance shifting from one region to the next. We have gone from not knowing how the energy gets up there at all, to watching it arrive and beginning to weigh out the different ways it comes. That is enormous progress. It is also not the same as a finished answer. And the people who study this are perfectly comfortable saying so, because in science, Knowing exactly where the edge of your understanding lies is its own kind of achievement. I find that genuinely restful rather than disappointing. We reached out and touched the oldest question in solar physics, and instead of snapping it shut, we learned to see it more clearly. The corona is still keeping a little of itself back, and a small machine is still out there falling close again and again, gently asking. Now, you might be thinking that this is all very lovely, but very far away. A puzzle about a distant star. Fascinating perhaps, but with little to do with your life as you lie here tonight. And I understand that. The sun feels like scenery, like something painted permanently into the sky, warm and constant, and entirely separate from us. But it is not separate from us. Not really. And this is the part I most want you to carry with you. The sun does not only shine, it breathes. It has moods. It moves through a long, slow rhythm, a cycle of roughly 11 years, swinging from quiet stretches when its face is calm and nearly spotless, to active stretches when it is restless and stormy and covered in dark spots. The Parker Solar Probe launched during one of the quiet times and flew its closest, deepest passes during one of the active ones. So it has been able to study the sun in two very different tempers, calm and stormy, which is a gift the mission's planners hoped for but could never guarantee. We have been watching that rhythm for a very long time. People noticed dark spots on the face of the sun centuries ago. Once we had instruments gentle enough to look without harm, and for generations, no one knew what they meant. Then, in the 1840s, a patient amateur astronomer named Heinrich Schwabe, who had been quietly recording the spots day after day for years, noticed that their number rose and fell in a steady cycle, swelling and fading over roughly a decade, and then beginning again. He had uncovered the heartbeat of the sun, its long, slow pulse of activity, simply by looking carefully every clear day for a very long time. It is, once more, that same quiet shape of discovery. And when the sun is active, along with that steady wind we talked about, it sometimes does something far more dramatic. It throws. Every so often, the tangled magnetic field on its surface releases its tension all at once on a scale far larger than any nanoflare, and the sun flings an enormous cloud of plasma out into space. These great eruptions are called coronal mass ejections, and a single one can carry billions of tons of magnetized plasma racing outward across the solar system. Most of these eruptions sail off into empty space and trouble no one. But now and then, one of them is aimed more or less at us. And a day or two later, that cloud of plasma reaches the Earth. When it does, we are not defenseless. Our planet has its own magnetic field, an invisible shield of its own wrapped around the whole world, called the magnetosphere. And when the cloud from the sun arrives, it meets that shield and slides around it, and most of its energy is gently deflected away into space, the way it has been for billions of years. The Earth has been weathering the sun storm since long before there was anyone here to notice. This is an old relationship, and the planet knows how to handle it. What we do notice is the beautiful part. As that plasma slides around our magnetic shield, some of it funnels down toward the poles, into the upper atmosphere, where it makes the air itself glow. We call that glow the aurora, the northern and southern lights. And here is a small, lovely secret about those colors. They come from the very air we breathe. As the particles from the sun strike the gases high in our atmosphere, they make those gases glow, and each gas shines in its own particular hue. Oxygen, struck high up, glows green, the most common color of the lights, and higher still, it glows a deep red. Nitrogen adds its own soft blues and violets along the lower edges. So those slow curtains of color rippling across the night sky are really the sun's storms meeting the Earth's own breath, the wind from a star lighting up the air above our heads. It is the most gentle and gorgeous face of space weather. And there is a quiet grandeur to how the auroras work. When the sun flings out one of those great clouds of plasma, it does not arrive instantly. It travels for a day or two or three, drifting across the gulf between the sun and the Earth, so that the lights in our sky are really the late echo of a storm that left the sun days before. And when the glow does come, it comes to both ends of the world at once. The same gentle curtains that ripple over the far north are mirrored, in that very moment, over the far south, the two polar skies lighting up together, north and south, like a single breath taken in two places. They ripple and fold and shift because the magnetic field high above us is itself shifting, alive and restless, shaped by the wind pressing against it. The whole planet, wrapped at both ends in slow, silent light. In the last couple of years, as the sun has moved through the most active stretch of its long cycle, those lights have been reaching much farther from the poles than they usually do, glowing over towns and fields that almost never see them. It is possible that you saw them yourself, or that someone you know did, and shared a photograph of a sky lit up in colors it does not normally wear. If so, you were looking at the solar wind. You were watching the far end of the very story we have been telling all night, arriving quietly over your own horizon. There is, of course, a more practical side to all of this, and it is the reason scientists watch the sun so closely. A strong enough storm from the sun can do more than light up the sky. The most famous example happened long ago, in 1859, before electricity had truly entered daily life. A tremendous storm from the sun swept over the Earth, and the auroras it caused were so bright and reached so far that people saw them glowing near the equator, in places that had never witnessed such a thing. The only real technology of the age that felt it was the telegraph, whose wires crackled and sparked under the storm's invisible touch. It was, more than anything, a wonder. But it was also a quiet warning, because we now live in a world far more woven through with technology than the telegraph operators of that century could have dreamed. The truth is that our modern world is woven through with delicate technology in a way no earlier age ever was, and much of it quietly feels the sun's moods. A strong storm can blur the navigation signals our phones and planes rely on, can scramble certain radio communications, can force flights over the poles to find new routes. It can even reach the satellites in orbit. A few years ago, a fairly modest storm warmed and puffed up the upper edge of our atmosphere just enough to drag down a batch of newly launched satellites before they could climb to safety, and they were lost. None of this is cause for alarm as you lie there. These events are rare, and the people who watch the sun are very good at their work, and the systems we depend on are more resilient every year. Once, in 1989, a strong solar storm briefly disrupted the power grid across part of Canada for several hours. These events are uncommon, and the world has grown far better at preparing for them. There are people whose entire work is to watch the sun, at places like the Space Weather Prediction Center, keeping a steady eye on our star so that when a storm is coming, there is time to get ready. But the storms are the reason we would very much like to see them coming. And this is where our distant mystery and our daily life turn out to be the same story after all. Because the better we understand the wind at its source, deep in the corona where it is born, the better we can forecast what the sun is about to send our way. A spacecraft flying through the corona is not only chasing an ancient question about heat, it is also, in a quiet way, a weather station at the very source of the weather, helping us read the moods of our star a little earlier, so that when a storm is coming, the people who keep the satellites and the power flowing have time to get ready. The probe that flew into the sun to satisfy our curiosity is also gently helping to keep the lights on in your town. So the next time you feel the warmth of the sun on your face, or you happen to catch the sky glowing in colors it should not have, I hope you remember that you are not watching something separate from you. You are feeling the edge of an enormous, active, breathing star, one whose moods reach all the way to your skin and the air above your home, and whose stranger weather we are only now learning to read, with the help of a small machine flying through its atmosphere. When you think about it, almost everything that has ever lived has lived on the sun's gift. The green leaf turns sunlight into food, and everything that eats the leaf, and everything that eats those, is living on captured sunlight, passed along. The warmth that drives the winds and lifts the rain and stirs the oceans is the sun's warmth. Even the ancient fuels buried deep in the earth are sunlight, gathered by plants ages ago and pressed down into stone over unimaginable time. The sun is not only the light in our sky, it is the quiet engine behind nearly everything, the source of almost all the energy that has ever moved through living things on this world. We are, all of us, in the most ordinary daily way, children living on the steady generosity of a star, and that machine is still out there. As this is being told, the Parker Solar Probe is still flying, still looping out and falling back in, still making its close passes by the sun, gathering more of its quiet record each time. A spacecraft built to last only a few years has kept going, returning to the fire again and again, sending home its data between dives. The exact details of its final passes and how long it can keep enduring the heat are part of a story that is still being written even now, in real time, far above our heads. No one knows yet how the very last chapter of this mission will read. It is still happening while you rest. There is something wonderfully alive about that. So much of the universe we talk about is finished, ancient, light that left its source before there were people to see it, stars that died long before our world was born. But this is happening now, right now, tonight, while you lie there in the quiet. A small spacecraft with a living scientist name on its side is out there beside the sun, having truly entered its atmosphere, and the wind it studies is streaming past the earth, and somewhere a sky may be glowing softly with it. You are not hearing about something that ended long ago. You are resting inside a story that is still going on, one whose next chapter has not yet been written, by people who are still out there watching, still asking, still learning. And one day, of course, the mission will end. Not in disaster, most likely, but simply in the quiet way that all missions end. Its fuel for nudging itself will run low. Its instruments will fall silent, and we will stop hearing its small voice from beside the sun. But the spacecraft itself will not vanish. That tough little shield, that froth of carbon that stood against the star, is expected to endure, and the probe is expected to keep circling the sun long after it has gone quiet, looping around and around on the path it traced for us, a silent monument drifting forever near the fire it once flew into, long after everyone who built it is gone, long after we have forgotten the particular numbers and dates. It may well still be there, going around, a small made thing keeping the sun company in the dark. There is something deeply peaceful in that thought, a quiet companion for our star, left behind by a curious species, circling on and on. We have come a long way tonight, from an ordinary fact about a campfire, to a man who was doubted, to a green light that turned out to be a million-degree secret, to a machine that touched a star and lived, to the gentle realization that the sun's distant fire reaches all the way down to the warmth on your own skin and the colors in your own sky. So let the facts go now. You do not need to hold on to any of them. The numbers, the names, the dates, they have all done their work, and you can set them down one by one, like setting down a bag you have carried a long way. There is nothing left to learn tonight, and nothing left to remember. From here, you can simply rest. Let me invite you gently to soften. Let your shoulders ease down, away from your ears, into the bed beneath you. Let your jaw unclench, and your hands lie open and loose. Let your breathing slow just a little, without forcing it, the way the breath naturally lengthens as sleep begins to come. There is nowhere you need to be, nothing you need to do. The night will take care of itself, and so will the sun, and so will the small machine drifting beside it. You are allowed now to do nothing at all. Let that softening move slowly through you, if it likes. Start far away, at your feet, and let them grow heavy, sinking into the bed, no longer holding anything at all. Let that heaviness rise gently into your legs, into the long muscles that carried you through the day, and let them loosen and let go. Let it spread into your hips, into your back, each part settling a little deeper into the mattress beneath you, supported entirely, holding nothing up. Let your belly rise and fall on its own, easy and slow. Let your hands lie open. Let your arms grow heavy and warm. Let your shoulders, which carry so much without ever being asked, drop down and rest at last. And let it reach your face, the small muscles around your eyes softening, your jaw loosening, your forehead growing smooth, until your whole body lies quiet and unguarded, like a still field under a night sky, like the calm surface of the dust-free zone wrapped around the sun, swept clean and peaceful and asking nothing of you. We spent the whole night walking up to one strange and beautiful question. Why is the corona so much hotter than the surface that feeds it? And we found in the end that we do not entirely know. The sun has let a small machine fly straight through its atmosphere, has let us cross the very edge of it and touch the star, has let us measure its wind and watch its magnetic field fold and snap, and still it keeps a little of itself back, quietly, the way it has for billions of years. And I want you to feel, as you lie there, that this is all right, that the not knowing is not a failure. It is a kind of room, a spaciousness left in the world. The sun does not owe us its secrets, and there is something gentle in being allowed to live beside a mystery without having to solve it tonight. You can let the question stay open. It has been open for 100 years. It was open while you were a child, and while your parents were children, and long before that. It will keep softly until morning, and long after you and I are gone. There is comfort in that, if you let there be. Some things are simply larger than a single night, and they ask nothing of you but to rest beneath them. Let yourself drift toward it for a moment, not to study it, just to be near it. The sun is so large that the mind cannot really hold it. If it were hollow, you could pour more than 1,000,000 Earths inside it and still have room to spare. 1,000,000 worlds like ours, each one with its oceans and its mountains and its slow rivers and its quiet sleeping cities, each one with someone lying in the dark just as you are now, all of them swallowed up inside a single star, with space left over. That is the scale of the thing we are talking about. That is the fire at the center of everything we know, the fire that every planet circles, the fire that has poured out its light for billions of years without once pausing. Let your breathing find the slow rhythm of it. There is no need to change anything, only to notice. The breath comes in gently and goes out gently, the way the sun's wind comes and goes, the way the tide rises and falls, the way the long cycle of the star itself swells and quiets over the years. Perhaps, if it happens on its own, each breath out grows a little slower and softer than the one before, sinking you a little deeper each time, the way the probe sank a little closer to the sun with every patient loop. There is nowhere you need to arrive. You are already here. You are already resting. And the great slow breathing of the cosmos, the wind from the star, the turning of the worlds, is breathing right along with you, in no hurry at all, carrying you gently down toward sleep. And into all of that immensity, we sense something the size of a small car. Picture it now, as small as it truly is. A little machine, no larger than the car parked outside, wrapped on one side in a few inches of white carbon, falling through the atmosphere of a star that could hold 1,000,000 Earths. It is almost nothing against that brightness, a speck, a grain, a single mote of metal and silicon, the smallest, most fragile thing, set against the largest, most powerful thing in our sky. And yet it is there. We put it there. With patience and care and 60 years of dreaming, with a man's quiet stubbornness and another man's brave decision to publish a doubted paper, with the work of thousands of hands, we reached out from this small blue world and set a tiny machine beside the fire. And the fire let it stay. The fire let it pass through and held it gently and let it go again, unharmed. So picture it drifting there now in the bright, endless light. All around it, the plasma streams and glows, the great quiet fire of the sun pouring outward in every direction, the same wind that Parker imagined, the same wind that blows the tails of comets always backward across the dark. And in the middle of all that light, the little machine moves calmly, tucked into the cool shadow of its own shield, its instruments resting at the temperature of the room you are lying in. It is bathing in the very birthplace of the solar wind, in the source of the warmth that reaches your skin on an ordinary afternoon. And it is holding, gently, the things it has seen, keeping them safe in the dark behind its shield, waiting, patiently, for the moment it can turn its small antenna back toward home and tell us, in its plain and simple way, what it found. There is no hurry in it. The machine does not rush. It simply drifts and gathers and waits and holds what it knows in the quiet until the time is right to share it. It has all the time in the world. And so, tonight, do you? Let the night float back past you now, softly, the way images drift through the mind just before sleep, with no effort and no order. There is the campfire on the cool, dark field, and the warmth fading as you step away. There is the green light in the corona, the ghost we called coronium, a 1,000,000-degree secret hidden in a single color. There is the young man at his desk, certain of a wind no one believed in, and the comets overhead with their tails blown always backward. There is the rocket rising in the dark before dawn, and an old man, 91 years old, looking up to watch his name climb toward his star. There is the small machine falling, year after year, looping past Venus, drawing closer to the fire. There is the long silence of a Christmas Eve, and then 2 days later, a single faint tone crossing 8 minutes of empty space to say, "I am here, I am all right." Let them all drift by, those pictures, soft and unhurried, asking nothing of you. You do not need to hold any of them. Just let them pass, like slow clouds, like the wind itself, moving through and away. And as those pictures drift away, let the wind carry you with them. Imagine yourself growing light, light as the dust near the sun, light as a single breath of plasma, drifting out on that endless gentle current, out past the warm familiar Earth, out past the pale crescent of Venus, out toward the great golden fire and the small bright machine drifting beside it, and then on, past even that, out across the vast quiet dark, all the way to the far shore of the sun's atmosphere, where the wind finally grows soft and thin and gives way to the stars. There is no fear in the drifting, only the slow, weightless ease of being carried somewhere immense and gentle, somewhere that has been there all along, waiting, patient, vast, and entirely at peace. You are floating now on the breath of a star, going wherever it goes, holding nothing, needing nothing. And the wind keeps blowing, out past the machine, out past the bright corona, out across the dark between the worlds. The solar wind streams on, the way it has since long before there were people, the way it will long after. It washes past Mercury, it washes past Venus, and in time, soft and unfelt, it reaches the Earth and slips around our own quiet magnetic shield, and somewhere far to the north it touches the high air and makes it glow green and red and violet. All of it happening right now while you rest, all of it carrying on without needing you to watch. You can let that be a comfort. The wind does not need you to follow it. The machine does not need you to stay awake. The sun will keep its long fire burning whether or not you are watching, the way it has every single night of your life, the way it did before you were born, the way it will after. There is nothing you need to hold up, nothing you need to keep going. The whole enormous gentle machinery of the heavens turns on its own, and has always turned on its own, and you are allowed now to simply be carried by it, the way a small boat is carried on a slow and patient tide. So let go of the oars. There is nothing to row toward tonight, and nothing to row away from. The current knows the way. It has known the way for billions of years, long before there were any of us to wonder about it, and it will know the way long after. You can take your hands from the water and simply lie back in the little boat and let it carry you, the stars wheeling slowly overhead, the warm wind of the sun at your back, the night unhurried and kind around you. Every worry you carried into this room can stay behind on the distant shore. They will keep until morning. They always do. For now, there is only the slow water and the wide sky and the gentle motion of being carried, and you growing softer and heavier and farther away with every breath. And here is the last thought I want to leave drifting with you before the words begin to fade. Everything you are made of came from a star. The iron in your blood, the same iron that glowed green in the corona and told us its secret. The calcium in your bones, the oxygen you are breathing slowly in and out right now, the same oxygen that glows green in the northern lights. All of it was forged in the heart of some star long ago, in fires like the one the little machine is drifting through tonight, and then scattered across space when those stars came to their ends, and gathered up again over billions of years to become the Earth, and the oceans and the trees and the slow rivers and you. You are not a visitor to this story of stars and wind and fire. You belong to it. You are made of it. You are, in the most literal and gentle way, a small piece of an ancient star, grown somehow into something that can lie in the dark and wonder about the sky it came from. So when we reached out and touched the sun, in a small way, we were only reaching back toward where we came from. A child of the stars, sending a small machine home to the kind of fire that first made it, just to see, just to be near it, just to understand a little more, and then bringing back a single quiet tone that meant, I am here, I am all right. You are here, you are all right. You are a small, warm, living thing on a small blue world, resting tonight beneath a sky full of the same fire you are made of. And out there, beside one of those fires, a tiny machine with a kind man's name on its side is drifting through the light, holding its secrets gently, in no hurry at all, asking nothing of you. There is nothing left to do, nothing left to understand. The question can stay open. The wind will keep blowing. The machine will keep drifting. And you can let go of all of it now, slowly, the way the ancient dust near the sun simply, gently disappears into the light. Let your breathing slow a little more. Let your thoughts grow soft and far away, like the sun seen from the very edge of the solar system, small and warm and no longer urgent. Let the bright fire and the little machine, and the long blowing wind, and the green light, and the quiet beacon, all drift away to the edges of your mind, until they are only a faint warm glow, somewhere out in the dark, keeping on without you. You do not need to follow them anymore. You only need to rest. There is nothing left that needs you tonight. The sun does not need you to understand it. The little machine does not need you to remember it. The wind does not need you to feel it pass. Every great and small thing we wondered about tonight is carrying on perfectly well on its own, out there in the kind and patient dark, and not one of them is asking anything of you. You have done enough today, more than enough. You can set it all down now, the whole long day, the whole long week, the whole weight of being awake in the world, and let it drift off with everything else, out toward the soft far edge of things, leaving you here, warm and quiet and wonderfully, finally, free to sleep. You have come all the way to a star and back tonight. You can stop now. You are warm. You are safe. You are made of the same gentle fire that fills the whole sky, and it is still out there, drifting, glowing, blowing softly past you, asking nothing of you at all. Just drift. We are almost at the end of the night, and there is nothing waiting there but quiet. Tonight, we flew into the sun. We went all the way to the strangest place in the solar system, to the crown of fire that burns hundreds of times hotter than the surface beneath it, and we found, just as the old puzzle promised, a place that still quietly defies the physics we thought we understood. And rather than fear that, we sat with it. We let it be beautiful. We met a man who saw the solar wind before anyone believed him, and who lived long enough to watch a machine carry his name toward the very star he spent his life trying to understand. We followed a green light that turned out to be a 1,000,000-degree secret. We built something small and brave and wrapped it in white carbon, and we let it fall for 6 years toward the fire. We crossed the very edge of the sun and touched a star. We waited through a long, quiet Christmas, and we heard it answer with a single tone that meant it had survived. And we drifted with it through the bright plasma, close enough to touch the fire, and humble enough to admit how much it still keeps to itself. We built a machine to touch the fire. We watched it survive the impossible, and we brought a small piece of the mystery home. Thank you for spending your night here, drifting through the cosmos with us. If you drifted away somewhere in the middle, long before the beacon ever sounded, then the night did exactly what it was meant to do, and there is no better ending than that. And if you would like to be carried off like this again, to another corner of the universe, on another quiet night, you are always welcome to follow along. We will leave a light on, somewhere out in the dark, and there will always be another journey waiting, another star, another mystery told softly, another night to drift. But that is for another time. For now, there is nothing left to do, and nowhere left to go. The machine is safe beside its star. The wind is still blowing gently past us, and you are here, and you are warm, and you are made of the same quiet fire that fills the whole sky. Sleep well, rest easy. We will see you on the next drift through the cosmos. From all of us at Cosmic Drift, good night.